What's up, everybody? In this video, we're going to cover USACO's 2022 January contest at the bronze level. Problem number 3, drought. Let's read it together. The grass has dried up in Farmer John's pasture due to a drought. After hours of despair and contemplation, Farmer John comes up with a brilliant idea of purchasing corn to feed his precious cows. Farmer John's N cows, which is between 1 and 10 to the 5th, so at most 100,000 cows, are arranged in a line such that the ith cow in the line has a hunger level of HI. So for example, if I've got my cows lined up, I have cow 1, cow 2, cow 3, cow 4. If their hunger levels happen to be like 6 and then 5 and then 7 and then 9, then if I were to say cow I equals 3, that's just referring to the third cow. So for I3, then the hunger of I, which would be the hunger of cow 3, would be equal to 7. So that's what this HI is indicating. We have a hunger for each one of the cows. The hunger level is going to be between 0 and 1 billion. This is an important thing to note, and we'll come back to why that's important later. But just for now, note that the number of cows is up to 100,000 and the maximum hunger level is 1 billion. As cows are social animals and insist on eating together, the only way Farmer John can decrease the hunger levels of his cows is to select 2 adjacent cows, I and I+1, and feed each of them a bag of corn, causing each of their hunger levels to decrease by 1. Okay, so what that means is that if we have 2 cows that are next to each other, and if I do like bars to represent their hunger level, then if I were to feed this cow on the end here, I must feed its neighbor. If I were to feed this cow on the end here, then I must feed its neighbor. But if I were to feed one of the middle cows, I have a choice to feed either the left side cow or the right side cow. We're going to find a way to make it so that we don't have to worry about making that choice. And the way we're going to do that is by processing it from left to right. We'll come back to that later as well. So we feed each of them a bag of corn, which would be a total of 2 bags of corn. This is worded a little awkwardly, but we're not splitting a bag of corn between 2 different cows. We have 2 adjacent cows, each which will get 1 bag of corn, which will count as 2 total bags of corn, which also means the number of bags has to be an even number. So this is causing each of their hunger levels to decrease by 1. The reason that decrease by 1 is important is, remember we talked about hunger being 10 to the 9th, which is 1 billion. 10 to the 9th is so large that if you were to feed them 1 by 1, even if we only have 2 adjacent cows and they're each 10 to the 9th and 10 to the 9th, if we feed them 1 bag at a time, we'll go over our runtime limitation just getting those 2 cows fed down. Not to mention the fact that not only do we have up to 10 to the 9th hunger, but we have up to 10 to the 5th cows. So we are going to need to find a way that doesn't involve looking at comparing every cow to every other cow. We also are going to need to find a way that doesn't involve subtracting 1 at a time. Farmer John wants to feed his cows until all of them have the same non-negative hunger level, which means we don't know necessarily what that hunger level is, but we're not feeding them down to 0. So that's another thing that's a question mark, is we don't know what hunger level to aim for. Otherwise, it'd be a lot easier. If we knew what hunger level that they're going to get fed down to, we could just figure out the difference of all of them from that hunger level, and we know how many bags of corn it's going to take. Since we don't know what that number is, as we work our way down, we're going to have to try and figure out when they're going to meet together. Please help Farmer John determine the minimum number of bags of corn he needs to feed his cows to make this the case, or print -1 if it is impossible. Okay, let's look at our input and our output restrictions here. Input format comes in from the terminal, so it's just typed into the console. Each input consists of several independent test cases. This is a little bit of a newer thing. Essentially, what this is doing is one single test case actually has multiple test cases. Depending on your language, there are little adjustments you can make to how you approach these problems to make that not really a big deal. And I'll probably make a video to cover that in particular, because this is something that has caused a lot of confusion for a lot of students. But you know, again, essentially, once you have a good way to approach this, it doesn't really affect how you solve the problem at all. So we have several independent test cases, all of which need to be solved correctly to solve the entire input case. The first line contains time 1 through 100, giving the number of test cases to be solved. Okay, so that's like this right here, 5. This means that there will be 5 test cases to solve within this one test case. The T test cases that follow, each described by a pair of lines. Okay, so here's a pair of lines describing 1 test case, 1 test case, 1 test case, 1 test case, 1 test case. The first line of each pair contains N, So for example, 3 is N in this case, 6 is N in that case. And then the second line contains the hunger level of hunger 1, hunger 2, up through hunger N. So in this case, 8, 10, and 5 is the hunger levels for the cows in the first test case for those 3 cows. Here are the hunger levels for the 6 cows in the next test case, and so forth. It is guaranteed that the sum of N over all test cases is at most 10 to the 5th. We don't have to think about that too much, but that's a runtime complexity thing. It's just letting you know that they're not all going to be 10 to the 5th. Even if we had 100 test cases and each test case had 10 to the 5th cows, we still would be pretty close to being able to pass this within time complexity, but it'd be getting a little close to running up to the edge. But they're telling us that the total number of N is only going to be 10 to the 5th, so we don't have to worry about that. Output, we're going to just print the output to the terminal, and it says, please write T lines of output, which means every single one of these test cases is going to have exactly 1 output. And then those lines of output are going to represent how many bags of corn were necessary. It says, note that the large size of integers involved in this problem may require the use of a 64-bit integer data type, e.g. a long and C++. It does. It's not may. It does require this. If you're doing Python, you don't have to worry about it. For C++ and Java, you'll have to look into how to get something that's larger than an int. The reason why is that an int data only goes up to about 2.1 billion, which means that if you are getting above 2.1 billion, then you're going to overflow the integer and then you get bad data. So that's why we need 64-bit integers. Okay, so let's look at this first one here, this first part of this first test case, which is 8, 10, and 5. 8, 10, and 5. So with a little fiddling around, and actually right now would be a good time to pause the video and fiddle around with this and see if you can draw out some cases and see if you can get a feel for how this problem works while I fix this number 8. All right, so we have to solve this problem. Couple things that we can make as far as observations. The first is, since we know they have to all be equal and their hungers can't go up, then if we get the minimum of all these numbers, we know that 5 is going to be the highest possible. It's got to be at least 5 or less that we get everybody down to. Another thing to note is if we feed this first cow that has 8, there is no way to feed this cow without feeding the neighboring cow. This neighboring cow, the second cow, is just along for the ride. So knowing that the minimum is 5 and knowing that the first one is 8, I mentioned before, we don't want to have like feeding 1 bag at a time. We won't get there fast enough. We have to be able to decide on multiple bags. We know that this end cow here has to get down at least to 5. So we know that we can do 3 bags all at once. And we know that next minus 3 is going to happen right to its neighbor right here. So I've got minus 3, that brings us down to 5 and 7. Now, since the first one here has matched the minimum, we won't be subtracting from it anymore. When we subtract from the second one, we'll have to subtract from that and whatever its neighbor happens to be, which actually happens to be the minimum and happens to be the end. Now, in a minute here, we'll fiddle around with these bags and see how ultimately this isn't going to be a problem. We're not going to hit a situation where you might be saying and say, well, this is 5, 7, and 5. It's symmetrical, so I should subtract half from here and half from here. Actually, as it turns out, because of the fact they're both going to get lowered, it doesn't even matter what order you do it in. So for the 7 here, we have to get the 7 down to a 5. So we're going to do minus 2 here. We'll go ahead and take both of those minus 2 off the end one here, minus 2, which is going to bring us down to 3. Whenever we hit a new number that's lower than our minimum as we're going through, we should make a note of it. So here, because of the fact I subtracted to get this one down to 5, that lowered this one down to 3. I'm going to make a note that my new minimum is 3. I'm going to finish, though, with my previous minimum being 5. I'm going to run through the rest of the list till I get to the end. Then I'm going to have to start over and now work with a minimum of 3. So starting back on this side, I've got 5. I have to subtract 2 from that to get that down to 3, which means I have to subtract 2 from the neighbor to get that down to 3. This now is the minimum. This is the minimum. This is the minimum. And we're finished. They're all equal to each other. So let's look at how much we subtracted. I did minus 3 and 2 here, which is 5. I did minus 3, 2, and 2 here, which is 7. And I did minus 2 on the end, which is 2. If I add all these together, I'm going to get 14. And then if I go check the sample output, 14. I got 14 for that first case. So that is the correct answer for that one. So I mentioned that symmetry thing, the left and the right. Let's look at just starting from 0. If I were to start from 0 and feed cows, what ends up happening? If I were to feed, let's say I feed 2 bags to the middle, like that, and then 2 bags to the edge here. And then I'm going to feed 2 bags to the middle again, which brings me up to 4, and 2 bags to the edge here, 2. Now, I've got 2, 4, and 2. If I were to split left and right and say, okay, I've got 4 here, I'm going to lower this one down to 3 and lower this one down to 1. And then I'm going to lower the middle one down to 2 and lower this one down to 1. You'll notice that they only got closer together. So I've got 2, 1, and 2. If I were to subtract from the first one again down to 0 and the second one down to 1, then if I were to subtract from the first and the second one, then I go down to 0 and 0. If I back that up and I do 2 at a time, if I know the minimum is 2, if I were to subtract 2 from this one all at once, getting down, then I would have to subtract 2 again from this one, and then 2 again from this one, and they would all be zeros. We can process this from left to right. Let's look at that one more time, processing left to right. Okay, if I start with my minimum equal to 2, and I look for anything that's 2 or higher than 2, I find this one, I see that's higher than 2, so I subtract 2 from it to get it down to 2. And then I have to subtract 2 from this one to get it down to 0. Then I have the 0, which is my new minimum. I start back over here. This is going to be 2. I'm going to subtract 2 from that to get it down to 0. And then I'm going to subtract 2 from the next one to get it down to 0. So regardless of what order we do that in, we end up with the same result. If we had only one bag, so I'll start over here, here, 1, 1, 1. Let's do 1 and 1 like that. This will be 1 and 1. And then I'll do 1 and 1 here, which will give us 2 and 1. I have a minimum of 2. First one that's larger than that is this. So I subtract 1 from this one and 1 from the next one. That's going to give me a new minimum of, or sorry, the minimum should have been 1. To subtract 2 down to 1, that's going to zero that one out. It gives me a new minimum of 0. If I were to start back over here, this is equal to 1. So I have to subtract 1 from that and 1 from the neighbor, and they all become zeros. So whether the difference is by 1 or by 2, and whether I subtract it all at once or whether or not I do it left to right, I'm going to get the same end result. So what we can do then is we can use that as an approach to solving these problems. Essentially, all we need to do is, I'm going to do that first one again. Essentially, all we need to do is figure out our minimum equals 5 in the left to right, lowering each bar so that it's at least down to the minimum. If we lower that one to 5, we got to lower this one to 7. And if we're going to lower this one from 7 down to 5, we got to lower this one down to 3. That gives us a new minimum equals 3. We'll finish up and start over. This is 5, so we're going to have to subtract 2 to lower that down to 3. We'll subtract 2 again to lower that one down to 3. Now, one other thing to watch out for is there are certain problems that are unsolvable, and you have to recognize that. If we look down at the sample test case, it shows you there were 3 that have negative 1s. That is this case here, this case here, this case here, and this case here. So let's look at this one that's 10, 9, 9, 10, because this is actually a really important problem, 10, 9, 9. Now remember, whenever we work on the ends, we always have to work with the neighbor. So if I were to add 1 to this end, I have to add 1 to the next one next to it. If I were to add 3 to the end, I have to add 3 to the one next to it. There is no way that I can ever make this one be larger than this one. I can make the middle be larger than the edge because I could add to the middle and then add to the other side and make the middle taller. But there's no situation where I can make this be taller because I can't add anything to this without also adding an equal amount to that. So when we have 10, 9, 9, as soon as we realize that, let me draw this out. We'll even watch how that's going to play out if we were to try and solve that. 10, 9, 9, we would have a minimum of 9. We'd see that this is equal to 10, so we do minus 1 from here, bringing that down to 9. But then that would bring this down to 8. Then this 9 over here, we can't really subtract from it because now it's gotten too high. But every time I subtract from this, if I go this down to 8, this will go down to 7. If I were to get this one down to 7, I could get this one down to 6. Any subtracting I do on the end is just going to make the middle go down even faster. But no matter what I do, the end here will never be able to. So any case where you've got an item on the end, whether it's the left or the right end, that's larger than the one next to it, the problem is not solvable. That same thing applies here. This one is on the right, that's larger than the one next to it. There's no way to get that 2 down to a 1 without lowering the 1. Also, if you ever hit a situation where you've got something that's above the minimum, but subtracting would cause either of the ends to go into the negative, that's also not solvable. Essentially what you're doing then is in analyzing these numbers, you're finding your minimum, you're running through and identifying anything above the minimum. Let's do it with the 464 as last one, 464. So if my minimum is equal to 4, we run through and find anything that is greater than the minimum. So the 6 is greater than the minimum. We subtract whatever we need to subtract, and we want to kind of jump our way down to the minimum. This I mentioned before that the highest hunger level would be 1 billion. We can't just subtract 1 and go from 1 billion down to 0. It would take too long. We have to be able to subtract in jumps. So we'll subtract all the way down to the minimum. In this case, I'll do -2 and -2. That's going to give us 4, 4, 2, 4, 6, 4. We'll make a note that our new minimum is going to be 2. We'll continue on through looking for anything above the old minimum, which is 4. We'll find this one, which is 6. So we'll do -2, -2. We'll have 4, 4, 2, 4, 4, 2. We finished. So now our new minimum is going to be 2. 4 is larger than 2, so we'll subtract 2 from this and 2 from its neighbor. 2, 2, 2, 4, 4, 2. Proceeding on, we find the next one that's above the minimum, so we'll do -2, -2. And then we'll go 2, 2, 2, 2, 2, 2. Now they're all equal. I've subtracted 4 total here, 4 total here, 4 total here, 4 total here, which adds up to 16, and that was the answer for the first one. All right. So yeah, looking for situations where an end is higher than the middle, and then otherwise running through. And just remember, when you have your bars here, I'm just going to draw a couple random sized bars. Essentially what's going to happen is starting from the side, assuming the side isn't the minimum, you're going to lower that down to the minimum and then subtract the same amount from the neighbor. Now that this is the minimum, we're not going to touch this one. So we're not going to look to the left. We're just going to move forward. This one needs to be lowered as well, but we have to lower this one and the one after it. We can't lower this one and the one before it because the one before it's kind of already solved down to the minimum. So we lower this one down to the minimum. That's going to affect the next one. We'll continue lowering everything down to the minimum so that it's a tie with that minimum, subtracting whatever we need to do. Oop, in this case, I made an unsolvable one because I made an end that was too high. Once we get to the end, whatever our new minimum is, we make another pass, lower everything to that minimum again. Whatever we need to do that, lower the next one down to the minimum and so forth. If anything goes into the negatives, or if one of our ends is too high, then the problem's not going to be solvable. Alrighty, good luck coding it, and I'll talk to you in the next one.